This video is about material or product testing. Now, testing of materials is obviously very important to ensure that the designer or the manufacturer has chosen the right material based on its properties. Products could also be tested to ensure that they can live up to their sort of life expectancy, or the quality of the materials during manufacture has been up to the standard required. Now this can be broken down into two broad sections, obviously destructive and non-destructive testing. Now in destructive testing, one might be testing a material and recording things like the indentation, how much it bends or breaks, or potentially the wear of the material as it's being sort of abrasion tested, for example. One form of destructive testing is to test the hardness of an object. Now, hardness is obviously the ability of a material to resist wear or indentation or scratches, for example, by another material. Now, hardness is often a byproduct of strength. So basically, if a material is stronger, then it's often harder. It's not necessarily always the case, but this is a good rule of thumb. Now, there's three basic methods of hardness testing. The first is the Brunel test, whereby a hardened steel ball is forced into the surface of the material by means of a load, and obviously the indentation is then measured to calculate how hard that material is. The second test is the Vickers test, very similar to the Brunel test, but this time it's using a diamond pyramid to indent the material, producing obviously a different shaped indentation, and then a microscope is used to determine the hardness based on the indentation again. And then finally the Rockwell test. Now this is more appropriate generally for quality control testing of a finished product, and basically a probe or device is touching the surface of the material, and the indentation or the hardness value rather is indicated on an attached dial, avoiding the need to measure a smaller indentation as found in the Vickers or Brunel test. Materials can also be tested via impact tests to demonstrate how tough the material is. So toughness is obviously the ability to withstand a sudden impact or a mechanical shock, such as being struck by a hammer or something similar. Okay, and it's basically the what you're trying to find out from this test is the property to see how brittle the material is. So whether the point that the material will fracture or break under a sudden force. Now there's three main methods of impact testing: the Izod test, the Sharpie test, and the Hounsfield test. Now in all of these tests they are sort of variations of the same sort of thing, but basically a striker or hammer is driven at the specimen piece or the piece of material at a set rate, and again there are many constants in this test, such as the mass of the striker, the size of the test piece, and obviously how it's held needs to remain constant for different materials. And what you're generally testing is the ability of the product to absorb the impact. Now the tougher the material is, obviously the more it will absorb the impact without fracture or breaking. Another form of destructive testing would be tensile testing. Now by putting a material under tension, you can get information regarding its tensile strength, so the ability to withstand sort of forces in that manner. Elasticity, which is to do with a material being able to be stretched and return back to its original form. Plasticity, which obviously relates to ductility and malleability, and obviously these are the material's abilities to be formed either by drawing the material or squashing it, pressing it under a compressive load. Now in tensile testing, generally a piece is attached between two grips or vices, if you like, or clamps, and one of the grips is fixed in position while the other is attached to a slider, which is operated by a motor that can then obviously pull the two sides of the material apart under a constant tension and a constant rate, until either it's going to break or get past its yield point, which is obviously the point where it becomes completely plastic and can be deformed, or it stretches beyond the limits of the machine, and thus the test sort of demonstrates some of the elasticity of the material there. The last two forms of destructive testing I'm going to talk about are wear resistant and fatigue testing. Now in wear resistant, it's obviously testing the wear or how long the product can last under sort of like an abrasive force. Now this is determined by obviously rubbing the material with an abrasive. Now this is often a weighted disc of the material, so for example you might be testing perhaps clothing to see how long it will resist wear, so from daily use. or it could be on brake discs, for example, where you're rubbing an abrasive disc against the material of number times at a given pressure, and it will probably give you an idea therefore of how long this product will last under that sort of constant wear in a similar sort of situation. This is also found in the pottery industry, but as opposed to testing the sort of the clay, you're testing effectively the abrasive resistance of a glaze applied to it. And obviously this is tested with something similar to a knife type tool, because obviously this is the sort of load that you'd expect if someone was eating from a plate from a daily basis. As with wear testing, fatigue testing is kind of testing the product in a similar sort of situation to what it'd be used by, to the point where it effectively fails or breaks. Now, one example of this might be the wire used in tyres. This can be held between a vise and twisted in sort of different directions until the point where it becomes brittle and then breaks. Another example of this you may have seen in IKEA, whereby their chairs quite often are placed under a pad which is powered by a pneumatic cylinder to simulate that seating environment. So it's obviously applying stress to the sort of structure of the chair, and this happens over and over again to kind of determine how resistant it is to fatigue in its normal daily use. In contrast to destructive testing, there are obviously non-destructive tests as well, which can obviously be conducted on products to find out if there's any flaws or near surface faults with a product. Now, some of this requires quite specialist, sophisticated machinery or equipment, but others can even be carried out in a day-to-day basis in the workshop. So surface cracks, for example, could be found by sound and touch. So simply running your fingers across or looking at the object could determine some sort of defects, but also they can be rung. So if you think a bell can be rung, but it will only ring truly if it is not cracked or if the surface is undamaged. So by striking a product lightly, you can detect whether there's perhaps some sort of fault in the product there, as well as obvious visual checks or touch to sense these faults directly. Another way of testing if there's any cracks or anything is to apply liquid into the material or on the material, and any excess material can be removed, leaving any penetrating liquid on the actual cracks to kind of highlight them. Okay, these, to make them a bit clearer, you could apply a light chalk to these as well, or dye, and this will show where the cracks are placed. In the case of metal products such as castings, magnetic testing is sometimes employed to find defects such as cracks and hollows can be found just below the surface. So the component is magnetised, making it part of an electrical circuit, and iron particles are then dusted over the area, which then highlight where the magnetic lines of force are broken, thus showing up a defect. In order for cracks to become visible in steel products, sometimes it's necessary to pickle the solution. Now, as the term implies, it involves acid, in this case a weak solution of sulfuric acid, heated at 50 degrees centigrade for a number of hours. Now, this will take off the oxide layer that's found by the combination of oxygen and the steel on the surface of the material washed off, and thus this will make the surface crack clearer and easier to detect. Both light and sound can be used to detect faults or indicate faults within the body of the material. In its most basic sense, light is used often in the pottery industry to see through some sort of partially transparent materials like bone china to indicate faults. Now, slightly more technically, you can also use X-rays and Y-rays, or gamma rays as they're sometimes called, to see into materials. Now, X-rays can obviously penetrate a material like rubber or fabric to detect perhaps air bubbles between layers of rubber in a tyre, for example. Now, for more thicker or denser materials such as steels or irons, the Y-rays or gamma rays can be used to detect these faults. Now, the issue with this obviously is safety as a consideration. Therefore, protection needs to be applied using concrete or lead-lined walls where these rays are in action. Finally, as stated, sound can also be used to determine whether there are cracks or defects in the internals of a material. So very high frequency sound vibrations can be used to define these. So ultrasonic frequencies, somewhere between 500 and 100 megahertz, are used. So by using a probe, passing it over a material such as like a strip sheet of material used in sort of aircraft, or perhaps even in tyres and things like this, or pipelines, the probe is passed over the material. Normally the vibrations will pass all the way to the rear side of the material and then reflected back. So if there's a differentiation between this and what is expected, you can understand there would be some sort of defect within the material.